calculation for the surroundings, we're going to use MC delta T. So whatever we take the temperature of, that is our surroundings. So that's for our surroundings. And then, for the heat change, so whatever our system is, we will use this. So this is for what change occurred. Is there two R's in occurred? Because the energy in the universe is constant. The change in energy for our system will be equal to in magnitude, but opposite sign of our change in energy in our surroundings. So we're going to use these three. Yeah.
What did we take? What does that say? Like, what did we take? What did we take?
What did we take temperature of? Temp.
Oh.
Okay, everybody's okay. Who wants to write up here?
Oh,
See how pretty it is. A couple of things you've got to remember. This change will depend on how much of your system you used. So the magnitude of our delta H will depend on the quantity of our system that was used. And as a result, you will see a corresponding delta T. So types of calorimetry questions. Let's go simple. Dissolving of a solid. In water. So dissolving of a solid in water. In this case, what are we going to be taking the temperature of? Inge? The water. So the water will be our surroundings. What will be the system? The solid. Another type of calculation could be a chemical change where we're mixing two solutions together. So this is going to be a chemical change. It could be, for instance, an acid and a base. Or it could be another type of double displacement reaction. This type of question is going to be a little bit tricky because you've got two solutions. So your total mass for your calorimeter is going to be the mass of both of them. Okay? So in this case, your Q will be your liquid quantity, but your delta H will be outlined in the question. For instance, it could say, what is the molar enthalpy of neutralization for the base? What is the molar enthalpy of neutralization for the acid? The question will actually tell you what the system is. And then the third one, combustion of a fuel to heat another substance. So for instance, you could be heating heating a liquid in a pot. By burning a fuel. Could be propane, it could be those liquid burners that you get for heating trays. What would be the system, what would be the surroundings for these, for this last example? Could be like you're heating hot chocolate in a copper pot on your stove, or on a barbecue, or on a camping fuel. What do you think is going to be the system? What's going to be the surroundings?
Would the system be burning with fuel?
Yes, so your system would be your fuel. And what would you be taking the temperature of?
Substance?
Which substance?
The one that you're burning, the liquid?
Not burning, because that's our
Heating.
system. Whatever we're heating, and it could also be the pot. It could also be the pot. So there's your problem. So you've got to figure out what quantities go with which calculation. So the first thing you should do is identify your system and your surroundings, because that's going to help you group the quantities. So what is our system in this question? What is our surroundings?
The lithium chloride, and the surroundings is the water, right?
Yeah. So here is our system. So that's going to be our delta H. And the water is going to be our surroundings. When you calculate your Q, the mass will be the mass of what you are taking the temperature of. You're not going to add the lithium chloride to the water. It's just going to be the mass of the water. So we're going to do Q first. So we've got 100 grams. .1, I forget what your textbook is it 8 or 9? 9? Joule, gram, degrees Celsius, and your temperature change, T final minus T initial. So now we know delta H, we can find moles, we can find molar enthalpy. So we're going to substitute our values. In here, this is what we're trying to solve. Trying to solve for our molar enthalpy. So you need to find the moles of lithium chloride. What's the molar mass of lithium chloride? 42.39 grams per mole, thank you. And now, solve for delta H. Say it again, negative
34,060.535.
535 at the end. All right, that's joules per mole. Let's change it to kilojoules per mole. So you would divide that by 1,000, because there's 1,000 joules in a kilojoule. And how many significant digits should we have? Okay. There you go, negative 34.1 kilojoules per mole.